All right. Good morning, good afternoon, good evening, good whatever it is for you right now. Today we're going to be taking a look at an interesting little integral problem that is going to involve Taylor series that will allow us to find the answer. So I want you to consider the indefinite integral of x cosine of x minus sine of x, all that divided by x squared and integrated with respect to x. Now, if you want to pause video and give this integral a shot, and then if you want, you can come back and see how I attacked it. All right, so since this doesn't appear to be an easy substitution or a simple antiderivative, so you'll find that the answer is actually pretty nice. So if you were familiar with some weirder functions and their derivatives, you could potentially recognize this. But my first step was simply to split this up, seeing as we have a subtraction in the numerator and we only have a monomial in the denominator. We can split this into two integrals. So this is the integral of x cosine of x over x squared, integrated with respect to x, minus the integral of sine of x over x squared, again integrated with respect to x. So you'll notice here on the left that this x divides out with one of the powers of the x in the denominator. So we're just left with cosine x divided by x for this integrand. So now we're left with two integrals that are just a trig function divided by some power of x. And the question is, how do we attack this? Well, you may recall that sine and cosine have relatively simple Maclaurin series that we can use to represent these functions, and they're convergent for all real numbers, which is very convenient. So we can rewrite cosine x as the sum from n equals 0 to infinity of -1 to the n, x to the power of 2n, all of this divided by 2n factorial. And then again, we're dividing this whole thing by x, and we're integrating with respect to x. Similarly, the sine function can be rewritten as the sum from n equals 0 to infinity of -1 to the n, x to the power of 2n plus 1, all divided by 2n plus 1 factorial. We're dividing all of this by x squared, and we're integrating with respect to x. All right, so now that we have converted sine and cosine into polynomials, if you will, this makes this pretty easy to deal with. As I said, this is all a string of polynomials here. And if we're dividing this by a polynomial, or a monomial that is, with the same variable x, essentially just dividing that out from each term, and we can reflect that pretty easily in the sum. So this entire integrand is going to become the sum from n equals 0 to infinity of -1 to the n, x to the 2n minus 1, since we're dividing out a single power of x, and 2n minus 1 is 2n minus 1, if you will, and all of that is still divided by 2n factorial, and we're integrating with respect to x. On the right, it's a pretty similar story. The sum from n equals 0 to infinity of -1 to the n, x to the 2n minus 1. We're dividing out two powers of x here. 2n plus 1 minus 2 is 2n minus 1. All that divided by 2n plus 1 factorial, and integrate with respect to x. Now this is lovely. As you may recall, summation works pretty well within integration, which is fitting because the integral is essentially just a confused form of summation. Since this is just a polynomial string, we can integrate it just like any other polynomial. So this becomes a sum from n equals 0 to infinity. -1 to the n stays the same, it's a constant. x to the 2n minus 1 becomes x to the 2n, since we add 1 power when we're integrating. Then here on the bottom, we're going to also have the 2n because we divide by that new power. And then the 2n factorial is a constant multiplier, so that stays the same. I don't need that integral anymore. That integral is irrelevant since we just performed integration, right? And instead I'm going to have a plus c in the front. I'm doing that in the front so I don't have to add extra parentheses in the summation. It should still be clear. It's just an easier way to write it. And similarly, for the integral on the right, we get the sum from n equals 0 to infinity. Again, negative 1 to the n as a constant stays the same. X to the 2n x to the 2n minus 1 becomes x to the 2n. We divide by 2n, and also the 2n plus 1 factorial in the denominator stays there because it is a constant. So now that we've performed integration, we simply need to make sense of this information. So the first step is to combine these sums into one sum. Since they have the same upper and lower limits, we can combine them under the same sigma. So we get sum from n equals 0 to infinity of the fraction negative 1 to the n, x to the 2n over 2n times 2n plus 1 minus negative 1 to the n, x to the 2n, all divided by 2n times 2n plus 1 factorial. So now we just have two fractions within this summation. So we just need to get a like denominator, common denominator, and subtract. Should be simple. It's a little tricky here though because we're dealing with factorials and n's, and it's kind of a mess. Let's recall here that 2n factorial is 2n times 2n minus 1 times 2n minus 2, so on and so forth until we have 3 times 2 times 1. Similarly, 2n plus 1 factorial is 2n plus 1 times 2n times 2n minus 1, so on and so forth. So the two of these are going to have all of the same factors, plus this here on the right is going to have an extra factor of 2n plus 1. So we know we're probably missing a factor of 2n plus 1 on the left. And then both of these share a factor of 2n. This means that our common denominator is simply going to be this denominator on the right, 2n times 2n plus 1 factorial. And this left fraction simply needs to be multiplied by 2n plus 1 divided by 2n plus 1, which we know is a form of 1. So this is the same thing as c plus the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n, times 2n plus 1 minus negative 1 to the n times x to the 2n. All of this divided by 2n times 2n plus 1 factorial. That fraction combination is remarkably easy to mess up, as I have discovered in the past. So now this is looking pretty nice and a lot easier to deal with. So again, we have c plus the sum from n equals 0 to infinity. And now we're going to notice we have negative 1 to the n here, negative 1 to the n here, x to the 2n here, x to the 2n here, which means we can factor out both of these terms. So I'm going to take both of those and I'm going to put them in the front. So we have negative 1 to the n, x to the 2n. And let's figure out what we have left. Here we're just going to be left with a factor of 2n plus 1, 2n plus 1. And here we're just left with a factor of 1 since we've factored out everything except for that 1, right? All of this divided by 2n times 2n plus 1 factorial. So it should be pretty obvious. This plus 1 and this minus 1 are going to divide out, right? So this is going to leave us with c plus the sum from n equals 0 to infinity of negative 1 to the power of n, x to the power of 2n, times 2n over 2n times 2n plus 1 factorial. It's all divided right there. So we can see here the fact that the 2's divide out, the n's divide out, the 2n divide out. So we've canceled out, divided out more properly, both of these terms, which leaves us with a pretty simple summation here. C plus the sum from n equals 0 to infinity of -1 to the n x to the 2m divided by 2m plus 1 factorial. So brilliant. We have integrated this expression and gotten an answer. But what does this really mean? You may recognize from before, this looks pretty similar to both the cosine and the sine Maclaurin series, right? The 2m plus 1 in the denominator of the 2m plus 1 factorial looks like it's from the sine, but the 2n here as the power of x looks like it's from cosine. But if you remember, if we add one more power of x, then this entire sum would simply be sine, which means that this entire expression is the same thing, this whole summation is the same thing as the sine function divided by 1 power of x. That is sine of x divided by x. So this is c plus sine of x over x. And sine of x over x is also known as the sinc function. That is sine with the c after it. And then, of course, plus c. So there we go. That is our answer. The indefinite integral of x cosine x minus sine x divided by x squared integrated with respect to x is simply the sinc function, which is sine of x over x. And you can verify this for yourself. You can integrate, or not integrate, you can take the derivative of this using the quotient rule, and you will get the integrand that we started with. So as you saw there, the Taylor series were really quite helpful in doing this, but the integration only took us a couple steps, and we spent more steps interpreting what we got out of the integration than we did actually performing the integration, which is part of the tricky thing if you're trying to use Taylor series to integrate. The information may be a little bit more difficult to process. That's all I have for you today. I hope you enjoyed, and if you have any questions or you want to see a video on any sort of topic, please let me know. Yep, that's it. Have a great day, and I will see you in the next video.